Now the current motor that's in here is just a AC motor, it's not a stepper motor, and it's controlled by using the buttons here on the side that raise and lower the Z-axis or the platform. And this is the Z-axis motor that is controlled by the buttons on the side of the machine. On the controller up here we have Z up and Z down, and also a focus button. So this upgrade will enable us to use these buttons to adjust the Z axis and also use the focus button. So the parts that I have to do this upgrade are firstly a lead shine stepping motor, and this model is a 57HS22-A. Now I'm going to be connecting that up to a stepper motor driver here, which is the DMA 860H. Now I also have a pulley gear for the end of the stepper motor and a stepper motor mount, which is a NEMA 23. Now, so that the bed doesn't get too low and hit anything, we're also going to be installing a lower limit switch, this proximity sensor. And if we get time, we'll also be installing the autofocus. As always, before you do any work on your laser machine, make sure that the power is off, and it's a good idea to remove it from the mains power supply. So I'm just having a look at my options here. We have the stepper motor and the mount that I have for that stepper motor, which is the NEMA 23. Now the holes for it don't line up with the holes already pre-drilled into the bottom of the laser machine, and it's also noticeably shorter than the previous mount. So I just want to see whether that's going to be an issue. We have our belt here, and want to see whether we can use the existing mount, and if we do, then all I need to do is drill out a couple of holes to match up with the NEMA mount, and then use the existing mount that was in the machine so that it lines up very nicely on the bottom. So something I noticed here was that the motor sleeve or gear that come with the original motor is larger diameter than the one that I have. So that would mean that I'd need to mount this motor back a little bit further to take up the tension that's on the belt. Or I can try, as I'm about to see whether I can fit this same motor gear onto the stepper motor that I've purchased. So what I've decided to do is use the motor mount that I ordered with my stepper motor, and I've mounted that there. But I'm using the gear from the original motor. The shaft size was identical, but the diameter was quite a lot larger, and therefore would give a little bit more tension on this belt. So now I'm just going to mount this into here and then get it all wired up. So now we've got the stepper motor installed, it's time to install the stepper driver. Now this stepper driver has a large heatsink and a fan on the back, so it can't be placed up against something, it needs good airflow. Now we've got the X and Y axis stepper drivers here, so ideally I'd put the Z over this side, but I've got the laser power supply which is a little bit too low, so I'm going to have to do some rearranging. Probably easier just to lift this up a little bit so that we can fit this in nicely, and otherwise I'd have to move the X and Y axis over a little bit so that we could fit it in over here. Okay, so with a little bit of shuffling I've moved the laser power supply up to make plenty of room for airflow here and around the back of the stepper driver. Now the stepper motor has got some short wires on it. It's a two-phase stepper motor, so we need to extend those wires so that they reach here. Now the stepper driver has 8 wires attached. This is a two-phase stepper motor, so we need to extend them so that we can reach the stepper driver. And I've just purchased this box of jump wires. It's a box which has got 6 different coloured rolls in it, and I'll put a link to this product that I purchased in the description below. It's just something that I purchased off AliExpress, and I find it extremely helpful and handy when you're using it to do the wiring with the different colours. But there's also 8 wires here, and we don't need all 8 wires to run directly to the stepper driver because we need to split them into pairs. So what you do to find your A and your B set, basically there is a wiring diagram here. So to find a set of paired wires for your stepper motor, what you need to do is go through them, and we'll just select the blue. we'll grab the blue one out and we use the multimeter on the resistance, and when we get a beep we know that we have a pair of wires. So that is a positive and a negative for that coil. So what we can do, we have here the blue and the red. So one of those will be the positive and one of those are the negative. We have a look at this wiring diagram here. We can see that the blue is split between a plus and the red to a negative. So the other pairs that would go with that would be the yellow and the green, and you can test those as well with the multimeter, but they are a pair. So what we're going to do is separate these into 4 different sets and then run those through to the stepper driver. So I just use this terminal block and I will sort the pairs out, and we'll go with A plus. And then the red and the green will be the and then those 4 wires we plug into the 6-pin Phoenix connector that plugs into the stepper driver, and it starts at this end, which is A plus, A negative, B plus, B negative, and then the voltage input for the stepper motor. So the yellow one on this we have as A plus, so we'll just wire them in. So with a bit of cable management as we go, we can just pop that in. So now we've got the stepper motor wired into the stepper driver here. So we've got our 2 pairs, the A pair and the B pair wired in. These last 2 outlets are for the power that will power the stepper motor, and we'll get that power from our 24-volt power supply. So we'll get a positive and a negative and pop it into that connector there. And then on this side, the signal, this gets wired up directly through to the Ruida controller board. So I'll pop a wiring diagram up on the screen, but what we have is a pulse and direction in a positive and negative for each. So on the stepper driver, it is labelled direction negative, direction positive, and then pulse negative and pulse positive. So these 2 positives, the white and the yellow, will get connected to the control board on the same socket, which is this 3-pin socket, and then we just have the pulse and the direction separate. So the negatives, or the ground of the pulse and direction, they get connected separately, but the mains, or 5-volt positive, gets connected together on this one and then separated for each on the other. Also, we're going to have a positive and a ground for the power to the stepper motors, and that will get connected, so we'll go do that now. So we have the positive and the ground that's been wired up to the power supply here. This goes into the socket that says voltage. So that goes into this socket here. So I'm using the negative as the first one and the outside one as the positive. And this is how I've also wired it up on my DIY machine. So if we do it the same, we should be fine. And the little wiring that I did earlier with these sockets, you plug into the signal on the stepper driver, and then that gets plugged in over here onto the controller board on the Z axis. So we have at the top of this socket, if we put it in the right way, we have our 5-volt input that's coming from the main board, and then we have the green being the pulse and the blue being direction. And if we follow that over to this side, we have the direction negative and then a positive, and we've got the pulse negative and then the positive. So those will get all cable tied up and made neat. So I've made this sleeve insert here to go on the inside of the ring. This ring is about 24mm and the laser tube, lens tube there is about 16mm. So I've made it so that it fits there nice and snugly on the bottom part of the lens tube, hard up against where the lens would be. So down here I've installed a proximity sensor so that when the bed of the laser or the Z-axis comes down and it reaches this point, it will stop and won't go any further so that it won't bottom out on the ball screws there. Now that's wired into the electrical compartment into the Ruida controller, and we'll have a look at the wiring of that in a moment. But up here we also have the Z-axis sensor, and to wire that Z-axis sensor up, it also runs along the X-axis cable chain and then along the Y-axis cable chain and then down into the electrical compartment. Now to fit the Z-axis focus pen, we put the ring on and put it down hard against the larger part of the laser lens holder. We then move the nozzle all the way to the top and lock it into position with the brass knob. Now those wires for those two sensors, as I mentioned, they go into the electrical component, and what we'll do is we'll pop a wiring diagram up on the screen to make it easier to see. So what we see here on this wiring diagram is connector 3 on the Ruida controller has connections or terminals 1 through 6, which is for the limit switches for Z and U. We're just looking at the Z limits, and if we look at the top, terminal number 1 is ground, and into that gets connected both the blue cables from our sensor switch. So that's our autofocus switch and our lower proximity sensor. The blue connections go into ground. Next we'll notice further down we have terminal 4, which is lat Z minus. This is our upper limit or our autofocus sensor. So we put into that one the black connection from the autofocus sensor, and into lat Z plus, which is terminal 5, gets the black connection from our proximity sensor for our lower limit. The next one down is PU-ZU. Now that is actually only a 5-volt output from the Ruida controller. The terminal that we're going to use for these two sensors is actually the 24-volt from connector 2. So at CN2 we'll see terminal 6, 24 volts, and into that one gets connected the brown cable from both the proximity sensor and the autofocus sensor. So let's have a look at the settings for the stepper driver and the stepper motor. So the 57HS22 stepper motor is rated at 4 amps and it has a step rotation of 1.8 degrees. So that's 200 steps per rotation. So first I want to set the dip switches on the DMA 860H stepper driver. So that's switches 1 through 3 to set it to the required amps. So in this case I set it to 3.71 to 4.45 amps by switching the switches here 1 and 2 off and leaving switch 3 on. Now switch 4 is not used and it's irrelevant on this stepper driver, so it doesn't matter whether you leave it on or off. My best option would be to use the lower speed on the stepper driver, which is this 400 steps per rotation. So using the table on the side there, I set switches 5, 6, 7 and 8 all to on. So that's at 400 pulses per revolution. So we need to set the Z-axis on the controller to be able to move the Z-axis freely without stalling the motor. So now let's have a look at the settings of the controller. So we'll look at RDWorks and we'll go into File, Vendor Settings. It asks for a password, RD8888. What we're going to have a look at here are the default settings that are on the Z-axis. So if we have a look at the Z-axis, which is this one here, we'll see that the default settings are 3.75 for the step length. We've got a breadth of 190 millimeters and those other settings there. So we're going to have a look at the motion of the Z-axis with the current settings that are in there. So we'll just read from the board to ensure that they're the correct settings that are saved in the controller, which they are. So now if we go over to the controller and we press the Z down button, now we haven't changed any settings, so we'll just see if the Z moves down. And the stepper motor stalls. It will also stall in the upward direction. So what we'd want to do is go back to RD Works and increase the step length. In this case, we're going to select, we'll double roughly, so we'll go to 6 and we will write that to the controller board and we'll test the motion of the Z-axis again. Okay, so it's moving down, but it's stalling on the up. So we'll increase the step length again to 8. And write that to the controller, and we'll do another test of the motion. Okay, so it's moving much smoother down, and we'll go back up. So that will enable us to move the Z-axis and take a measurement for calibration, and then we can calibrate these steps more accurately. So in order to calculate the steps required for the Z-axis, what we need is a fixed position. I'm going to use the bottom of the gantry as a measuring between the acrylic and the bottom of the gantry. So just using a ruler, if you want to be more precise, use some calipers or digital calipers. And we have 48 millimeters between the acrylic and the bottom of that gantry. If we have a look at the Z-axis here on the controller screen, it says that it's at 0. So we'll just write that one down because I'm prone to forget. That's 47 millimeters. And let's scroll down. We'll go down roughly 50 millimeters according to the screen. So we're at 30, 38, 39, 45. There's 50 millimeters. So if we measure that again, we have 132 millimeters. So 132 minus 47 is 85 millimeters that the Z-axis has lowered. The Z-axis here has recorded only 50 millimeters lowered. So we need to calibrate the 50 with the 87. So the way that we do that is we go back to RD Works. So in RD Works, we go to the step length, where we entered 8. Behind that are the 3 dots, press that, and we enter in the graph length. So the graph length is actually the distance that the controller thinks it's moved, which is 50 millimeters. But in matter of fact, it moved 85 millimeters. And then we press OK, and it's changed the step length to 13.6. We now write that to the controller. Okay, so now we've made that step length change. We'll just double check. We have 132 millimeters. Our Z-axis thinks it's at 50, and now we've written those changes. We'll erase the bed. We're just raising it up back to 0. So we're back at 0, and we have our ruler here. We've got close enough to 82.5, 83. We've got 82 millimeters, so 132 minus 80 is 50 millimeters. So we've actually calibrated our Z-axis. Now there are various methods of setting up the autofocus pen, and the method that I'm going to use is going to have a 5 millimeter gap between the workpiece and the nozzle. And then the autofocus pen, I don't want it too low, but I'm going to be setting it 5 millimeters between the tip of the pen and the tip of the nozzle. The other thing that we need to do is also change a setting in RD Works. So if we go back to RD Works, we'll see here that we have a home offset of 10 millimeters. This is just an offset from 0. It would add an extra 10 millimeters. So to avoid some confusion, I'm going to set this to 0. But while I'm here, I'm also going to change the speeds down to 5 millimeters a second, just so that it's not so fast when it's moving. Now we write those back to the controller board and we exit that. The next thing that I want to do is set up the autofocus. Now we have our Z-axis at 0. I've been playing around with it for a while and we've got it at 0, which means that we can't raise it any higher. So the thing we need to do is reset the X and Y axis, which will put Z back at 3000 because I'm not resetting the Z axis. So the X and Y is resetting. I'm not resetting the Z. So Z will allow us to raise it up higher again. So we now have 3000 on our settings there. what I want to do is raise the bed now so that we have 5mm gap between the nozzle and the workpiece. Now I'm just going to move this focus pen out of the way, because if it triggers the limit, we'll also not be able to go any higher. So we're just going to loosen the pen. So lift it up so that it doesn't activate. And we set 5mm gap there, probably touch tight. There we go, 5mm gap between the nozzle and the workpiece. Now if we go to our controller, we can go into menu, go across to function plus, press enter, and go to the diagnosis plus, and we'll see a set of triggers here. So for example, if I was to put a piece of metal on top of the x-axis, the limit switch will go on. The same goes for this z-axis here. So if I press down on the switch, the light will come on and I release. So what I want here is I've got my 5mm gap, so I want to set this so that we have the limit switch just activating and staying on, but not hard pressed. So we want it just as it activates, like that, and then tighten that and lock it in place. On the controller, if we press menu and go into the user settings, and if we go down to focusing, we can see that I've set the focus to 15mm. Now this 15mm is somewhere actually between 14 to 15mm, and that accounts for the 5mm gap that we have between our autofocus pen and the bottom of the nozzle. So that would bring it up to our 19mm, and we'll test that. So write that to the controller, and now escape, and we'll press the focus button. It touches the pen, backs off, and then it will go down from the pen an extra 15mm, which gives us a focal gap of 19mm. Now you're probably thinking, I can't do my math, that 5mm plus 15mm equals 20, but it's actually the 19 that I'm aiming for, and that is because there's a small variation between when the pen is activated and when it's deactivated. So there's a small variation there that you need to account for and measure.